part of a traditional Japanese folk mask is disappearing, then more and more become invisible, and finally only the burning pieces remain. That is the dissolving effect. An entire space dimension can be hidden and revealed partly when needed to make an interesting puzzle game. That is also the dissolving effect. In the game Genshin Impact, an enemy will turn into multiple particles and become invisible when getting killed. The God of Fire, Ifrit, chooses the similar style to escape from the battle in the game Final Fantasy VII Remake. They are all the dissolving effects. That will be the main topic in the 4th episode in the series Unity Shader Graph on Avalanche. Dissolving is one of the most popular visual effects in computer graphics, and there are many ways to implement it in the game. Today I'll show you my method, which relies heavily on the alpha property. The alpha value is commonly stored in the alpha channel of the albedo texture, and it can be multiplied with the alpha channel of the thin color to produce the final alpha. For objects rendered in the transparent mode, the alpha value will decide how transparent each point on their surface is. A low alpha value means more transparent, and vice versa. A high alpha value means less transparent. It's just simple like that. On the screen, I put two identical hanging hourglasses side by side. The front one has low alpha values so that you can see the sand inside through the glass layer. On the other hand, the hourglass on the back uses high alpha value and you can hardly see through the glass layer. You may see that this setup is used quite regularly when we want to render the glass, the bubbles, or the window. The alpha map can do much more than this. Let's take a look at this fence. You can see every little details of the wire clearly, and this beautiful model comes with a cost. It has nearly 700,000 vertices, which is absolutely not ready to be used in the game. In fact, it will be seen from a far distance most of the time. Then it's a great idea to use a low poly version when being far away, like this gold net. This trick helps a lot in reducing the poly count, especially when combined with a physically based clothes like the way this gold net interacts with the bone. In order to see through the fence and the net, we can set the alpha values of the empty areas at 0. But be aware, the pixels with 0 alpha will still be rendered and cost the power. For cut-out objects having multiple holes such as the fence or the gold net, we need a better way to not render those pixels. The alpha value can also be used to decide which pixel should be rendered and which one should be clipped or discarded. In order to do that, we need a threshold, a number to compare. That number is called the alpha clip threshold. Any pixels with the alpha value lower than this threshold will be clipped, and the rest will be rendered normally. Let's take a look at this grass texture and examine its alpha channel. With the threshold set at 0, all the pixels will be rendered, so your grass looks like a billboard. At 0.2, any pixel having the alpha value lower than that will be clipped, and the grass looks much better. Similarly, if we increase the threshold to 0.9, only the pixels having the alpha value greater than that are rendered. Part of the grass blades over here are missing, since they have the alpha value lower than 0.9. So, picking an appropriate threshold is important. Take this tree as an example of how the alpha clip threshold should be used. It looks quite good in every angle, but what makes it stand out is the number of vertices, only less than 800. The leaves are just multiple quads cutting out by the alpha clip thresholds. To sum up, the alpha property can be used to control the transparency or to decide which pixels should be clipped by comparing with a threshold, or to do both. No, you didn't hear it wrong. You can also use the alpha clip threshold in the transparent rendering mode. Let's take the window on the screen as an example. The glass is see-through thanks to the low alpha values. At the same time, the missing glass pieces can be discarded entirely if their alpha values are under the alpha clip threshold. It's much better than still rendering those pixels with 0 alpha. That's enough for the nerdy time. let's get your hands dirty. In this video, we will create a dissolving shader, letting the playing card disappear partly over time, like it is burning. You need to install Unity 2019.4 or above with a project using Universal Render Pipeline template, which is a URP. So let's take a look at the core idea of this shader first. We have just learned that the pixels are clipped if their alpha values are lower than the alpha clip threshold. So by having a higher and higher threshold, more and more pixels will be clipped. This effect is just about animating the alpha clip threshold over time and applying it to the object. Since the black and white texture may be hard to compare nearby pixels, I put colors on it for much better explanation. The pink and purple pixels indicate the lower alpha values, and they will be clipped earlier than the light blue ones. Imagine that we use that noise texture on the screen at the alpha map instead of the alpha channel of the main texture. What we get is the dissolving playing card, just by increasing the alpha clip threshold over time. This mechanic is so simple that the core idea diagram cannot be more compact. Before we begin, you need to download this stunning playing card from Thomas Flynn. There are an optimized 3D mesh and beautiful textures packed inside. Although this is a wonderful work, I cannot wait any longer to burn it down. Let's do it! The first two steps are creating a shader graph and creating a material associated with the new shader graph. Since we need the smoothness property, please use the P-Bar shader graph, and I believe that you could do it yourself. If not, please find my previous episode. From now on, any changes of the shader graph can be observed directly on the scene. And the next step is sampling the albedo texture. I hope that you're already familiar with this task, since it's done many times in the previous video. Just create the sample texture 2D in shader graph and set the texture you want to sample in the texture part. If everything's good, you should see the textures in the previous section of the node. Set it as a master node albedo. Now you can see the playing card in the scene if you assign the material to the mesh renderer in the previous step. And the next step is using the noise texture as the alpha map. For the noise texture, you can use any black and white noise one you like. I usually use the Möbius box to generate the noise I want. If you want to replicate the noise texture I use in this video, here are my parameters to create it in Möbius box. I'll put the parameters on the screen. Go back to your shader graph and use the sample texture 2D node to sample this texture. Since it will be used as the alpha map, you can pick any channel among red, green or blue to set it as the master node's alpha. It's a black and white texture, so the values of the red, green and blue are equal for every pixel. We're really close to the goal. Just one more step ahead is controlling the alpha clip threshold from the outside. It's literally just a number in the range from 0 to 1, so I recommend to make it a slider. After assigning it to the master node's alpha clip threshold part, you can try adjusting its value to see the dissolving effect instantly in the shader graph with the main preview panel. Now you just need to convert it to an expose property in the blackboard to control it in the inspector. There's something wrong with the edge of the card. Inspecting the original alpha channel of the albedo textures, you'll see that only the pixels inside the card are set to white. By replacing its alpha channel with the noise texture, we lost this mask. This will be our expected result for now. We want to replace the white pixels with the ones from the noise texture, while keeping the black pixels as black. Well, does it sound familiar? Indeed, it's the thin mask technique we used in the last episode. In order to achieve the expected result, we just need to multiply the original alpha map with the noise texture. The result is visualized on the screen. The problem is fixed by assigning this to the master node's alpha port. We now see the playing card shows and hides partly on our every adjustment of the alpha clip threshold in the inspector. Do you wonder why I chose to expose the unfocused threshold instead of animating it inside the shader graph? There are several reasons to do that. Firstly, I don't want the dissolving effect to loop. Secondly, I want to control the speed and the progress of the dissolving animation. Thirdly, while increasing the alpha clip threshold from 0 to 1 makes the object disappear, decreasing it from 1 to 0 makes the object appear. And the alpha clip threshold range will be different for each object or even different texture. There are so many ways to manipulate the alpha clip threshold, so it's much better to control it from the outside. Once again, I want to emphasize the importance of the core idea diagram. Since it gives you an overview before digging in, you should make your own diagram to plan your visual effect ahead, instead of spending hours struggling with choices. Congratulations! You've reached the 100 completion level of this task. Let's compare what we have in here with the outcome we wanted to achieve. Without highlighting the edge, our playing cards looks like a glitch. The glowing edge really takes the dissolving effect to the next level. Let's do it! When the alpha clip threshold increases from A to B, the pixel with alpha between A and B will change the state from being rendered to being clipped. Note that the pixel with alpha lower than A were already clipped before. On the screen, we can see that the pixels having the alpha values between 0.25 and 0.3 are highlighted. So if the alpha clip threshold is set to 0.25, we can consider the pixels with alpha from 0.25 to 0.3 as the edge. With our current implementations, the pixels having alpha higher than the alpha clip threshold are rendered with the color sampling from the albedo texture. In order to render the edge, we just need to set a color to the pixel having alpha in the range from alpha clip threshold to edge threshold. The edge threshold is defined by us, so we are free to decide where it should be set. The distance from the alpha clip threshold to the edge threshold is the thickness of the edge. To render it smoothly, I want to have it blend with the albedo in the edge area. Above the edge threshold, the albedo should dominate 100%. Our plan will be changed to the diagram on the screen with 3 steps. Here's the plan. In the first step, we will use the alpha clip threshold to clip the dissolving pixels like the current implementation. The second step is calculating the edge threshold by adding a small amount to the alpha clip threshold. The more we add, the edge area will be wider, so let's call this amount edge thickness. The final step is picking the color for visible pixels. 100% albedo for the pixel above the edge threshold, and a mix between the albedo and the edge color in the edge area. Specifically, the closer to the edge threshold, the more ratio of albedo will be put in the mix. The first step was done perfectly already, so let's move on to the next one. The next step is calculating the edge threshold. In order to perform the addition in shader graph, we will need the add node. The two input numbers will be added together to produce the sum in the output port. When assigning the alpha clip threshold and the edge thickness as the input, we'll get the edge threshold as the output. Just as simple as that. Now we have the two thresholds, let's use them to design the mixing ratio between the edge color and the albedo texture. This mixing ratio ranges from 0 to 1 as we knew from the second video of this series, so we need to remap these thresholds to the range of 0 to 1. By looking at this diagram, we can easily figure out this step can be done by converting alpha in the range of alpha clip threshold and edge threshold to the mixing ratio in the range of 0 to 1. Firstly, you will need a remap node. This node maps the value from a range of in min max to a corresponding value in the range of out min max. The out min max parameter, which is the target range, is already 0 to 1, so we don't need to do anything for this part. About the in min max, we need it to be in the range of alpha clip threshold and edge threshold, packaged in a vector 2 format, which is indicated by the green part. So let's create a new vector 2 with x equal to alpha clip threshold and y equal to the edge threshold, and then set it to the remap node's in min max part. the input value that we want to remap is the alpha value. So the remap nodes in port should be assigned with our alpha map from earlier stage. The alpha map values is converted to the mixing ratio. Now the next step is mixing the colors. I introduced this technique when we created a flashing Tron disk in the second video of the series, so I hope that you still remember it. It's just the love node with A is the first color we want to mix, which is our edge color, and B is the second color we want to mix, which is our albedo, and T is the mixing ratio, which should be assigned with the remap's output. However, the preview shows some strange colors. Don't panic, this is just a known issue that we faced once with love. We'll solve this issue really quickly. The cause must come from the mixing ratio, which is the remap node. Let's see what happens when we remap the alpha values. As we already know, the alpha value between the alpha grid threshold and the edge threshold will be mapped to a number between 0 and 1. So, how about the alpha value outside the input range? They will still be remapped with the same ratio to the values outside of the range 0 to 1. To be more specific, the values under the alpha grid threshold will be mapped to have negative value, and the values above the edge threshold after remapping will be greater than 1. Since the mixing ratio should stay in the range of 0 to 1, we must flatten the up range values somehow. It means the negative values will be set to 0, and the values greater than 1 will be clamped to become 1. We have exactly a node like that in shader graph to do this job, called saturate. Just put it between the part from remap to love, and the blending issue is fixed. And don't forget to use the love's output as the new albedo color. Ta-da! That's it! Now you have the proper distorting shader with beautiful edge highlights. It's so much better than the original version that is deserved to be considered as 150% completion level. Subgraph is a custom node which contains a graph inside. It's an amazing feature of shader graph. A subgraph can be used in multiple shader graphs just like a normal node. So, once you found a combination of nodes which can be reused in many places, such as PBR Avalanche, you can make it a subgraph. Then you don't have to recreate that series of nodes anymore. Moreover, a long chain of nodes will be replaced by a compact node. It makes the graph much easier to view and understand. The previous shader graph can be a headache to many people due to its tangled connections. Meanwhile, the dezooming effect is so popular that it can be used in different situations. These are the exact reasons why you should pack the dezooming parts into a subgraph. The shader graph will look like this when we're done, much cleaner than the current one. Any subgraph node can be seen as a black box to transform inputs to outputs. You just need to care about the inputs and the outputs while ignoring what is inside the box. The input is what we want to control outside the subgraph, so it includes the alpha channel from the albedo, the noise texture, the alpha grid threshold, and the edge thickness. I'll tell you my secret to quickly create these input ports. Unity will forward the black box properties from the shader graph to the subgraph to convert them into the input ports. So let's convert the textures and the colors to the exposed black box properties first. Then I will put all the alpha related operations into a subgraph by selecting those nodes, right click and choose Convert to Subgraph. A dialog will appear so that you can select a location to save this as a file. I name it _dezoom_subgraph to tell the purpose of this subgraph. a prefix of underscore letter have putting the subgraph in the top of the folder when sorting. A suffix of subgraph reminds me that this node is editable. In the shader graph window, multiple nodes are now replaced by just a single subgraph node. All the input ports we need are created. We just need to connect the corresponding nodes to these ports. On the other hand, the output ports are quite confusing since they don't have proper names. It's time to edit the subgraph. Select the subgraph, right-click and select Open Subgraph to see the nodes inside. It's so amazing that all the nodes we have just worked with a minute ago are here, maintaining not only their connections but also their positions. There are a special node with prefix out. It contains all the output ports of this subgraph. By clicking the small cup icon, a list of the output ports will appear. Now you can rename them. After saving this subgraph and go back to the shader graph outside, the output ports have meaningful names as expected. I want to rearrange the input ports to have the alpha on the top, and I want to have the alpha clip threshold as an output port for the cleaner graph. So I'll go into the subgraph by double-clicking the node, much faster than accessing the right-click menu. In the blackboard panel, all the input values are here because the blackboard properties and the input ports of the subgraph are the same. So if you want to edit the input ports, just edit the blackboard properties. I will drag the alpha property to the top so that it will be the first input port. About the output ports, I've made a new one to forward the alpha clip threshold. The data type of the alpha clip threshold is vector 1, so the new output port must have the same data type to be compatible. Go back to the shader graph outside and use the new output port as the master's alpha clip threshold. With our new custom node, the shader graph looks much cleaner now. In the GLTF version, this playing card has a smoothness texture. You can use another subgraph called PBAR Avalanche that I introduced in the second video to load all the PBAR properties you need. This shader will become much more useful because it can be applied to other objects as well. See the shader graph with these two subgraphs on the screen? Anytime you look at this graph, you know that this shader includes two big parts. Some nodes to deal with PBAR properties, and the other nodes perform the dissolving effect. It's easy to follow and ready to be upgraded. Imagine making a new shader from scratch to support all of these features. Both the volume of work and the final graph will give you long nightmares. Just apply this shader with another noise texture to the tron bar from the second video of the series. It will now disappear with style. If you're not interested in the PBAR stops, just throw the new subgraph into another shader and the dissolving effect is mixed in straight away. That's how powerful subgraph is. Definitely worth a 180% completion level of this task. The alpha map decides which pixels will be clipped first and which ones will be clipped later. It's made of a noise texture and the alpha channel of the albedo. So, if you want to control the dissolving direction, you need to modify this alpha map. A quick solution is to make another noise texture as shown on the screen. You need to rely on the UV map to create this directional dissolving map. In our case, the playing card image is upside down and occupies only half of the texture. There are too many downsides from this solution, making it not an efficient one. For example, you need to readjust many times to get it right, which is a slow iteration. If you want to change the dissolving direction, you need another alpha map. Or, if you want to change the noise texture, you need another alpha map. And the direction can hardly change during the runtime. In order to separate the noise texture and the dissolving direction, I would like to use an individual gradient texture to indicate the direction. I will combine them to produce a final directional dissolving map in shader graph. You can then pick any blending method you like to combine these two textures. My choice is the multiply node, just like the way we use it in the first version of this shader. With just a simple gradient texture, black at the top and white at the bottom, the produced alpha map can be used in a subgraph to make the playing card is shown from the bottom to the top. Note that the darker pixels will be clipped first. One more plus point of subgraph: when you update it, all the shader graphs using it will get the update too. Make this gradient texture exposed in the inspector, then you will find that it's super easy to change the dissolving direction by just swapping the gradient texture. Excellent! You should be proud of yourself after all of these hard work, since it's already 200 completion. In this video, I talk about the alpha and the alpha clip threshold properties. By animating the alpha clip threshold over time, we can make the dissolving effect. What if we keep the alpha clip threshold while animating the alpha map? The fire effect and the hologram effect can be achieved with this technique. Use your imagination to create your own effects with these new friends. I use the FBM2 type noise in this effect. Do you wonder why? Well, at first it just can be explained that this noise texture seems to match our intention of making a burning piece of paper. Behind the scene, 2 levels fractional Brownian motion noise is famous for creating smooth transition which repeats the pattern itself in different zoom levels. There are many types of noises. Each one is suitable for some specific effects. By digging into these noises, you'll spend less time looking for the right one. Shader graph provides some useful nodes to create the noise which is ready to use. Take a look at them. With only the shader we created in this video, any object can be dissolved. But the dissolved pieces look unnatural since they just disappear straight off. Visual effects are usually needed to cover this part by adding flying ambers. In Unity, we have another wonderful tool called Visual Effect Graph, which uses the similar node-based UI to the shader graph. Combining them really boosts the final visual effect. I use the visual effect graph to create the embers of the burning card. This is where a new problem raised. The amber particles appear both in invisible and visible areas. My expectation is emitting the amber particles only in the burning edge area. In order to do that, I need to synchronize the parameters between the shader graph and the VFX graph. Fortunately, we can do that with property binding mechanics from the VFX graph and the exposed black box properties from the shader graph. It's tricky just like how it's described, but the result is absolutely worth the effort. The burning edge looks aliasing because the nearby pixels were clipped. If we want to make a smoother edges, a better noise texture may not be enough. So I decided to create another shader to support the transparent rendering mode. In order to keep the semi-transparent edge, and in many other cases that the alpha clip threshold is unavailable, such as in sprite shaders, we need another solution to hide the dissolved pixels. The new subgraph is less complex than our implementation here thanks to the smooth step node. The shader graph is pretty much the same. If the transparent version of the dissolving shader is simpler and produce more beautiful effect, so why did I choose to talk about the opaque version? It's because the cost of rendering transparent objects is higher than rendering the opaque ones in general. By understanding the depth buffer and the rendering order of opaque and transparent objects, you'll understand my choice. I'll leave this part for you to explore. And don't worry, I'll talk more about this part when we learn to create the water surface, the outline effect, or the heat distortion effect in the future. The core concept behind this dissolving effect is very simple, but it can be extended and used in various ways. You cannot drag the alpha clip threshold manually to fade out the objects in the real game. Then how? By using animator, animation sequencer, or do twin, or blah blah blah. It's your choice. Which configuration could disable the dissolving effect temporarily so that it can be activated quickly later? By answering this kind of question yourself, you'll learn much more from this sole video. To sum up, the alpha property can be used to control this transparency, or to decide which pixel should be clicked by comparing with a threshold, or to do both. Secondly, by animating the alpha click threshold over time, we can make more pixels discarded to create the dissolving effect. Thirdly, the saturate node helps climb the values in the range from 0 to 1, and in order to highlight the dissolving edge, we need two thresholds to define the edge thickness and blend the edge color with the original unwidowed texture. And finally, as I promised in the earlier videos, our shaders are getting more and more complicated, so subgraph along with alignment, groups, and sticky notes helps a lot in making a neat shader graph. All your extra work will pay off some days. The technique I use in this video is just a single approach to create the dissolving effect. There are so many creative solutions out there too. You may not be able to learn and apply all of them. Just remember the core concept, manipulating the alpha with a threshold. As you can see, our core idea diagram is so simple at first, then it gets more complicated along the way. That is exactly why you should not procrastinate. Getting your hands dirty is the only way to find out what's missing and truly understanding how things work. In the Google Time section, I provided several keywords. These do not only help you to prepare for the upcoming challenges, but also give you some ideas to break the rules or create your own version of this dissolving effect. Hey yo! All the assets including the shaders, the particle effects, and the custom scripts can be downloaded from my Patreon page. I'll post another video to talk about the transparent version of the dissolving effect. Unless you want to miss it, please subscribe to this channel and you'll be notified when it's on. If you find something useful here and want to donate me, it will be my honor to show you the link in the description part. Otherwise, just a like and a share makes me happy already. What do you want me to talk about in the next video? Please leave a comment below. Thank you and see you next time on Our Balance.